If I show you this 28 by 28 pixel image, your brain instantly recognizes it as a circle. Even with small variations, the smart visual cortex of yours resolves these as representing the same idea. But can a machine do the same? Because to its brain or neural network specifically, that image isn't a shape but a list of numbers. So how does it go from numbers to understanding a circle or square or any other shapes? To answer that, we need to look inside the neural network. But here's the thing, while the architecture is something we designed and understood, what's really happening inside is still largely a black box, meaning we don't know what it does internally and all we have are our assumptions. So we focus on how these assumptions were made by understanding its architecture. Now, the idea of a neural network comes loosely from how our brain works, not in complexity but in one simple principle: connected units passing signals. In AI, those units are artificial neurons, and what they pass around are just numbers. In this video, we are going to use a standard multi-layer perceptron, which is nothing but a stack of input, hidden and output layers holding neurons that are arranged in this way. Their task is to recognize shapes. Let's say the input we are giving is a triangle as a 28 by 28 pixel image. What gets fed in the input layer are their pixel values. Each neuron holds the value of each pixel in that image, contributing to 784 neurons. The values are nothing but their respective grayscale intensity. It ranges from 0 for black pixels up to 1 for white pixels. Next, we have hidden layers, which can be one or many that holds certain number of neurons. Here, we can go with 60 neurons, and this is totally an arbitrary choice. The output layer specifically, we consider it as having 10 neurons as representing 10 different shapes. If the triangle gets fed in the first layer, it gets activated depending on brightness of each pixel. That pattern of activations flow into the next layer, creating another pattern and then another. Step by step, these patterns gets transformed until the final layer produces the network's prediction. This is how a neural network works in theory, but we'll try to interrupt this black box and understand the assumptions humans made based on neuroscience theories. If the input is a square, you and I decipher it by identifying edges, then from edges to patterns like corners, then identify whether it is a closed structure like a loop or curve or some others. Similarly, in the artificial neural network, a neuron might fire when it sees an edge, another when it sees a corner, or another remains idle when it doesn't see a curve. As this proceeds, the higher level neurons combines these signals to recognize the full shape. But this raises a deeper question. How do neurons learn to detect something in the first place? What kind of factors should they have? What knobs can it tune so the network can capture not just this pattern but any pixel pattern, like how edges come together to form corners, loops and other shapes? Well, we use a parameter called weight that acts at the connection between the layers. These weights are just numbers, random numbers at the beginning. The activations from first layer is taken and computed along with the weighted sum. For example, think of a neuron in the second layer taking all input values of a square and computes the weighted sum. This particular neuron, let's say, might give some importance for this edge region, and I want you to imagine that it converts all these weights into 0 except some regions with positive ones and do weighted sum. If only a small region has non-zero weights, then the neuron is effectively just adding up the pixel values in that region and ignores everything else. Or let's say if this neuron expects to detect more edges, what it might do is assign some negative weights in the low pixel value areas to classify whether it is an edge. These assumptions show how the weights validate importance, but it starts at random before reaching to this point. How it reaches, we will see that later. Sometimes the weighted sum gets inactive as it starts random, which eventually disrupts the network to proceed. To stop that, a term called bias is included. Bias basically prevents neurons from getting stuck by giving them a baseline level of sensitivity independent of the input. If you give a closer look at what the weights and bias are doing, they are working in a linear way of predicting things. For example, if I give some variations, like a hand-on square that is away from its training, it mostly gives the wrong answer. There should be some kind of non-linearity to be present because our brain solves most problems in a non-linear approach. The solution is to introduce an activation function, sigmoid in this case here. Sigmoid removes this linearity by introducing a logistic curve. Today's neural networks use better alternatives for sigmoid as an activation function. Okay, we are calculating the weighted sum for one neuron, but in practice, it takes place for all the neurons presented in the hidden layers, and this layer might successfully end capturing edges, the next hidden layer might end capturing corners, and so on, and reaches the output layer, where a term called softmax converts these raw scores into probabilities, which makes easier for the neural network to predict the output. Previously, I said the weight starts at random, so naturally, the network makes wrong predictions at first. To fix this, we show them the correct answer. The network compares its prediction with the truth and measures how wrong it was using something called a loss function. Then it slightly adjusts its weights and biases to reduce that loss. This process repeats again and again, each time getting a little less wrong until it starts to recognize patterns correctly. But this raises an important question. How does the network know which weights to adjust, and by how much? That's handled by a process called backpropagation, which sends the error backward through the network, assigning responsibility to each connection. Combined together, this allows the network to learn step by step, turning random numbers into meaningful pattern detectors. And over time, what started as noise begins to organize itself into something surprisingly intelligent. This is what happens inside a neural network. If we provide more training data for shapes and increase their learnable parameters, we get accurate predictions, but it becomes compute heavy. So a different neural architecture like a CNN is preferred over MLPs for image recognition, which can learn without much need of training data. If you want to understand about these architectures, or if you have any thoughts about the neural networks, leave it on the comment section and I'm happy to read all of it. If you enjoyed this video, a like and subscribe would really help the channel, and share it with someone who is interested in AI, tech or economics content. Thanks for watching.